The title is Work, Energy and Power, and the assignment is to make a revision of the topic. And I have already revision videos for every chapter on my YouTube channel, and it will be helpful if for any chapter you can visit that website, AS Physics Revision, that playlist actually, and you can access the playlist from the website also. The title of the chapter is Work, Energy and Power. This is the title of the chapter. I'm putting the first concept. There is nothing to copy actually, and the main thing is a quick revision. And the idea would be that I can ask some questions, and you people can also ask some questions so that we can have a quick revision. The first thing is the definition of the work. Work is the product of the force and the displacement in the direction of the force. Work is a scalar, and as a scalar, it is defined completely without any direction. So the first concept comes that suppose you want to move a chair. Okay, and if you want to move a chair, you will apply some force. Suppose you push the table and you push the chair, and the chair fall down. So it is not work now, because the force you applied is not in the displacement is not in the direction of the force. And in a way, you can say that the displacement and force should be in the same direction. So in physics, work is the product of the force and the displacement in the direction of the force. So force and displacement are in the same direction. Formula is W is equal to FD, and the unit is Newton meter, which is also called joule. Now, how we can define joule? 1 Newton, in physics, if you want to define a unit, the method is very simple. Just put 1, 1, 1 with every variable, like joule is 1, Newton is 1, and meter is 1. And then you make a definition. If 1 Newton, when unbalanced force acts on an object and produces a displacement of 1 meter in its own direction, the work done is said to be 1 joule. The emphasis, the emphasis of this technique is on 1. So when you say 1, it actually means that 1 is the main thing for this definition. So you have to put everything in 1. So 1 Newton, then you have to say 1 meter, and then you have to say 1 joule. So this is where the definition makes a sense in physics, that every quantity should be made 1. So 1 Newton, 1 meter, and 1 joule. You have to just connect them with a story. Now, what are the other units of energy? Kilowatt hour, electron volt, and mega electron volt. Okay. I have made the introduction. I have made some initial concept. I'm putting my first question. Kilowatt hour is used when the energy size is very big. Like our electricity bills, they come in kilowatt hour. Now tell me when electron volt is used. G, please answer when electron volt is used. Yes, Zen, can you reply when electron volt is used? Afra, can you reply? You can apply on the wrong chat also, Zoom chat. Mega kilowatt hour is used when the energy is big in size. Then logically, when electron volt is used, when the energy size is relatively small, like electrons, like positive particles, negative particles, microscopic particles. Electron volt is used for microscopic particles. Look at the energy conversion. For collisions, you're right, but actually electron volt is used for little particles. Electron volt is used for little particles, and kilowatt hour is used for bigger size energy conversion. So look at the energy conversions. Okay, so I move forward. Whenever in physics you make a graph, there are two parameters which are always there to look for. The gradient is always y upon x. The gradient is always y upon x, and the area is always y into x. Now look at this graph. Can you tell me what the gradient shows and what the area shows? Remember, gradient is y upon x, and area is y into x. Okay, what the gradient shows here? Does gradient show anything here? Quick reply is needed. Yes or no?
Gradient doesn't show anything.
Very good. Area is work. And what about gradients? Then does gradient show anything? Then are you there? No. Why you're on the chat now? Why you're not on the mic? Okay, fine. Anyway, your answer is right. Good. So the area is work. The line is horizontal. When the line is horizontal, it means force is constant. When the line is horizontal, the force force is constant. If the force is inclined, the force has to be resolved. This is a concept which is coming with us from the chapter number 1. When the force is inclined, the force has to be resolved. Look, I have resolved the force. Now, why I am taking FD cos theta? Why I am multiplying with FD cos theta? Why not sine theta? Because sine theta is the perpendicular component and cos theta is the parallel component to D. So we have to take a component which is parallel to D. So the logic comes F cos theta is parallel to D. F cos theta is parallel to D. This is an inclined force, and this is also an inclined force. Work is a measure of energy transfer, yet it is not necessary that all activities are work. Like if someone is doing maths and sitting on a table, obviously it's a brain drain and the person will be tired, exhausted. But in terms of physics, it is not any work. For example, physics says thinking is not a work because there is no displacement in the direction of the force. If you are standing holding your bag, it is not a work done. If an object is orbiting in a circle, look, this is the circular motion. In physics, it is not a work done. It is not a work done because the displacement is not in the direction of the the applied force. Now, there are some typical work values. Why this is necessary? Because estimation is another dangerous topic in our AS physics. How we can tackle this dangerous topic? Remember the rule when you're tackling this dangerous topic. Remember the rule that whenever you are looking for an unusual unit, joule is not our common life unit. We do not use it in our common life. So we need some values in our memory. Shutting a door is 5 joule. Throwing a cricket ball is 20 joule. Climbing the stairs is 1500 joule. Now a famous question comes, which has appeared. This MCQ has appeared around I think 3 times or 4 times in MCQ paper. What is the estimate the kinetic energy of an athlete? Estimate the kinetic energy of an athlete in a 100-meter race. So now please tell me, my next question for today, how can I estimate the energy of an athlete in a 100-meter race?
You take 70 kg as mass because that's the average mass of an adult. And then the speed can be 10 to 15 meters per second.
We can find the speed by speed is equal to distance upon time. We can find the speed by distance upon time, and then we can use the formula kinetic energy is equal to half mv square. In estimation, you can take any value which is realistic. I have taken 60 kg for the athlete. Speed is equal to distance upon time, and then I put the formula to find the kinetic energy. Work occurs at a microscopic level and at a macroscopic level. Microscopic level means molecules, ions, and other particles. Macroscopic means like ourselves, vehicles, other things. At a microscopic level, we refer to subatomic particle, molecules, ions, they collide, and they also do some work. The example here is the work done by a gas. The work done by a gas at constant pressure. Now, what is this formula? We have a cylinder and a gas is enclosed in a cylinder. A gas is enclosed in a cylinder. Now, you can see the piston and there is a pressure. There is a pressure on the piston. There is a pressure on the piston. Now, what happened? We allow the gas to expand. The gas molecules always collide with the piston, and it is possible that the piston moves out. We have a concept that gas molecules collide against a wall. When gas molecules collide against a wall, they rebound. When gas molecules rebound, the momentum changes. Momentum change is called impulse, and impulse upon time is pressure. This is in A level, the official explanation of pressure exerted by a gas. Why gases exert pressure? Gas molecule collide with the container wall, they rebound. After rebound, momentum changes. This is impulse. Impulse upon time is pressure. Now, the gas expands, volume increases. It's a frictionless piston. This is a change in volume. Now, pressure is equal to force upon area. Force is equal to pressure into area. So, work is equal to FD. Work is equal to F into D. So, you see the derivation that I have got pressure into area. You can see here that I got pressure into area into D. So I make A and D separate. In my O-level maths, I can recall that area into D is the change in volume, delta V. So when I put the change in volume, delta W becomes P delta V. Pressure becomes constant. Delta W is now delta V proportionality. And now it is a straight line graph and the gradient is pressure. The gradient is pressure. Now we come to energy. I will ask this is my next question for today. What is the definition of energy? Yes, Zen, please reply. What is the definition of energy?
Yes, sir. Sorry. Facing some issues.
What did you say?
So I'm saying I was facing some mic issues.
No problem. This is a small definition. You can write on the chat also. But obviously, mic using is convenient. So what is the definition of energy?
Sir, ability or force required some work.
What is the definition of energy? Energy is the
Capacity of
of doing work. The unit of energy is joule and it is a scalar quantity. Okay, we are here. Law of conservation of energy, our old friend, we saw this in our O level also. What is the law of conservation of energy? A very famous law. The law says that energy can neither be destroyed nor it can be produced, but it can be converted from one form to another. So this is one of the oldest physics rule and a fundamental rule that energy can never be perished. It can never be perished. It is always there, yet it can convert into other forms. No doubt, Einstein equation is equal to mc square challenged this law, but still for our mechanics version, the law is intact. Forms of energy. I'm putting the forms here and you can tell me the definition one by one. What is electrical energy?
The energy transferred by moving the charged particles.
The energy transferred, good. The energy transferred by moving charged particles. Second, chemical. I tell it, and the third, Zen will tell. Chemical energy is the energy involved in chemical reactions, which is regrouping of atoms in physics. Okay, now Zen, what is heat energy?
Yes, sir. So heat energy is energy that is transferred from one node.
No. It is the heat energy is a measure of kinetic energy of molecules. Mechanical energy, it is the energy required to move something. It is the energy to move. What is geothermal? Geo means earth. The heat energy present inside the core of the earth. It is the same geothermal, which is converting coal into diamond and many other conversions like lava, like geysers, etc. Volcano eruption. Tidal energy, which is now in discussion in many countries, which is the cheapest form of energy available. Tidal energy is the energy transferred by tides. Wind energy in the kinetic energy of air. Solar energy, the energy coming from the sun. The source of that energy is nuclear fusion. Sound energy, in which our Pakistanis are self-sufficient. Sound energy, the energy transferred by longitudinal waves. Now here comes some energy values. Why I'm showing that? Actually, the purpose of showing these values is to give an idea of some units, because you know the problem, Some units are in our common life, like kg, we know well, megapixel, pixel, the unit of air conditioner, like ton, we use them. Some units we do not use. I think you people might agree with me that in our common life, we never use the word joule. Joule is not a unit for us in our common life. Like even Newton, we do not use, but we use volt, we use ampere, we use watt, but ohm, the unit of resistance, is not our common life unit. So if you are dealing with a common life unit, some exposure is always there. Otherwise, what is the procedure? Remember some of the energy conversions to put an idea how to get another conversion. So for example, potential energy of person at top of stair, 1.5 kilojoule. So you can use it for another energy, missing energy unit. Classification of energy. There are two types, potential energy and kinetic energy. Again, energies are always at two levels. One is called microscopic level and second is called macroscopic level. When you talk about positron energy, it is microscopic level. When you talk about the kinetic energy of a car, it is macroscopic level. Now, potential energy, this concept has to be learned very carefully because it comes so much in paper. Remember, the energy stored in an object due to some work done on the object. For example, you have a spring and you stretch the spring, energy would be stored in it. This energy is called potential energy. So what is potential energy? Potential energy is the stored version of energy. Potential energy is the stored version of energy. This is the energy which is stored in something and it is due to some work done. In our course, there are three important potential energies: gravitational, electric, and elastic. Last year they removed electric potential and they shifted it to our A2. Now, gravitational EP, its definition is very famous. The concept is there. When you do some work in a gravitational field, like you go upstairs or an aeroplane is taking off, when you do some work against gravity, some energy is stored. Some energy is stored in the object, and that energy is called gravitational potential energy. Now, please, let me know the definition of gravitational potential energy.
Is it the energy stored in an object because of the work done?
That's a conceptual, and the definition was there. Gravitational EP is the energy an object has because of its position in a gravitational field. It is due to some work done against gravity. And the conventional formula delta EP is equal to mg delta h. And then we had a derivation. If you have a mass, you lift the mass against gravity. You need to do some work to move the object away from the earth. Now, work done is equal to force into displacement. You get the weight because you're lifting it. Remember, whatever potential energy you are doing doesn't matter. Remember the concept, every potential energy originate from a work. Every potential energy originate from some work. Why? Because energy is discussed a lot, but you will never see it. You will never see energy. You can see work. People say, I'm tired, I have no energy in our rough language. But actually, energy is something which is an entity hidden behind work. Work is the actual appearance of energy. Every every potential energy originates from some work done. Kinetic energy. Now I need its definition, and I have a confidence that this definition is very well known. Then can you give the definition of kinetic energy? Reply, Zain, you are looking a bit slow today.
Sir, I actually have fever. Sorry, connect.
Oh,
Sir, kinetic energy is the energy that an object possesses when it is in motion, or the energy an object has because of its motion.
very good. It is the energy possessed by an object due to its motion. And the one-time memory formula kinetic is half mv square. Derivation. We start with 2as is equal to v square minus u square. U is equal to 0. 2as is equal to v square and a is equal to v square upon 2s. So I find the acceleration. Then Newton's second law, F is equal to ma. I put the acceleration here and I got the formula. F is equal to mv square upon 2s. Then work is coming again here. Work is equal to force into displacement. You put the force equation into distance and you simplify. Now work will become kinetic energy, the same concept. Every energy actually comes for work. So work is a representation of energy. This is the derivation for kinetic energy. If a moving object accelerates or decelerates, if a moving object accelerates or decelerates, its kinetic energy changes half m v square minus u square. Look at the formula for change in kinetic energy. Now, if velocity is constant, kinetic energy is constant. So delta Ek will become 0 if an object is moving at constant velocity. The biggest example is our terminal velocity. So if something is moving at terminal velocity, kinetic energy will be constant and delta Ek is 0. Now, kinetic energy and momentum, a derivation actually. Half mv squared, momentum is mass into velocity, mv into v. And then you see mv is momentum. So kinetic energy is equal to half pv. Examples of energy conversion. These examples actually are coming from our past paper. Work energy power is a challenging chapter. Actually, they make very interesting cases there in the paper. Now, remember equations showing energy consideration. These are the equations which we have to make the rules. All energy losses on one side and all energy gains on the other side. Change in kinetic and change in potential. These are the formulas. Now, see this approach. When velocity increases, kinetic energy increases. So delta EK will be plus. When velocity decreases, kinetic energy decreases. When velocity is constant, kinetic energy is constant. Delta EK is zero. When something is going upward, delta EP is positive. When something is going downward, delta EP is negative. Horizontal motion, delta EP is zero. Work done by a driving force like a car engine is always on the side that contains losses, because work done by a driving force is actually a loss in terms of energy transfer. Work done against resistance, like work done against friction, it always comes on the side that contains the gain. Now I'm putting the examples. The first and the all-time famous example, if air resistance is ignored and an object is moving vertically, it is called free fall. Acceleration is equal to plus minus g. I'm putting the first case. The object is coming down. When object is coming down, velocity increases, height decreases. Velocity increases and height decreases. Now look at the formula. Loss in gravitational potential is equal to gain in kinetic. If we run this, we can get a derivation. V is equal to under root 2gh. There comes a very famous concept. All objects fall with the same acceleration if there is no air resistance. Case number 2, if you throw something upward, there is no air resistance. When you throw something upward, the potential energy increases and kinetic energy decreases. Fall with air resistance. Something is falling with air resistance, a very famous situation. This is called a viscous drag situation. Air resistance, when something is falling through air resistance opposes the motion, opposing the weight. As the object goes down, the velocity increases and the viscous drag opposition is also increasing. Air resistance gradually increases until air resistance equals the weight. Air resistance gradually increases until it equals the weight. Look, air resistance equals the weight. Resultant force becomes zero. Acceleration becomes zero. This is called constant or terminal velocity. One of the most repeated concept ever in our A-level physics. And what happens when something is falling through air? When something is falling through air, its acceleration decreases until the acceleration becomes zero, and so velocity becomes constant. This is the famous sketch. Look, the velocity is increasing at a decreasing rate. At the horizontal line, velocity becomes constant, acceleration becomes zero, and resultant force also become zero. Acceleration is decreasing. Acceleration is decreasing until resultant force becomes zero. Acceleration also becomes zero. Now, in this case, how we tackle energy? There's a loss in gravitational potential because you are coming down. So there is a loss in gravitational potential. there is a gain in kinetic plus work done against resistive forces like viscous drag. Now, as I said, there are two possible cases. The object has reached terminal velocity. When object has reached terminal velocity, then what happens? Kinetic energy will become constant, and then formula will become loss in gravitational potential is equal to work done against air resistance. It will limit. The formula will change. Look at this formula. This time, kinetic energy is not in the formula because change in kinetic has become zero. Loss in gravitational EP is equal to work done against resistance. Only that kinetic has gone. Solar cell, a lot of discussion is nowadays in our country and in the worldwide, they are now discussing it very seriously. This is a source of renewable energy. Solar cell converts electrical energy into, it converts solar energy into electrical. Solar panels, they convert solar energy into heat energy. An object falling in a fluid, when something is falling in a fluid like water, anything, when something is falling through a fluid, it experiences a viscous drag. It experiences a viscous drag, and due to the drag, it slows down. A car going up a slope, a car is going like a mountain ride, it's going upward. Now, here we come across a dangerous topic, inclined plane. Now, when you are facing inclined plane, one option is to make equation work done by the engine is equal to gain in potential plus gain in kinetic plus work done against resistance if you are accelerating upward. Second approach, which is very helpful, is to resolve the diagram, resolve the weight, and then solve the equation greater force minus smaller force logic. And this is then alternate method. Either you go by the energy equation or you go by the resolution method. Look at this resolution. Now it comes power. Okay, now I need my next question for today. What is power? Please give me the definition.
Power is the rate of work
Rate
done.
of work. Very good. Then your contribution. What is power?
Yes, sir. So I have recent experience. Power is the rate of
Power is the rate of doing work, and power is the rate of energy transfer. Power is work upon time, power is energy upon time, and the unit is joule per second. Joule per second is actually watt, and you can write it joule per second watt. Power is a scalar. Now, this is our definition for watt. Power is equal to 1 work upon time. So 1 watt is equal to 1 joule upon 1 second. So you can make a story connecting all of them. You can say if 1 joule energy is transferred in 1 second, the power dissipated is 1 watt. Estimate the power of a calculator, room heater, air conditioner, hair dryer, person climbing stairs. Actually, this is a type of memory to understand that these type of conversions are estimations are some way our memory. Calculator power is very small. In all the basic version of calculator, on the back side, they have written the power. Room heater, 1000 watt, air conditioner 1500 watt, hair dryer is 600 watt. These are all reference figures. How we can find the energy or sorry power of a person climbing the stairs? I had to we can simulate the situation. This is a staircase. It is approximately 6 meters high. These are all estimation. We have taken a person whose mass is 80 kg and it's rising up. G is equal to 10, and then we need to find power. Power is equal to mgh upon T. If we calculate, we get the power like this. Now, I have a graph of power against time. My question is there, what area shows here and what gradient shows here?
The area will be energy.
The area will be energy and gradient shows nothing. Area shows energy. Energy versus time. This time gradient shows power. It is a constant power because being a straight line, gradient is constant. Relation between power and velocity. It's like a derivation, and power is equal to work upon time, Fd upon T. D upon T is velocity, so power comes Fv. Power is equal to Fv, where F is the driving force, V is the constant velocity, and P is the power. This is a case where you can find the area. 1 upon 2 is coming here because area is area of a triangle. When it is a rough surface and you're taking something up, the formula will be applied, greater force minus smaller force. Look at the derivation and the working. F is equal to P upon V, and the downward forces are shown. Now, what formula you will use? Resultant force is equal to P upon V minus mg sine theta plus friction. Look at this diagram carefully. Efficiency. Efficiency of a system is the ratio of useful work by the system to the total energy input. Efficiency is power output upon power input or energy output upon energy input. For percentage, you have to multiply by the 100. Efficiency is actually a ratio, so it has no unit. There are two translations of power, power loss and power output when it is from power input side. For example, you're running a motor to lift a load at a constant speed. Speed is constant, so the kinetic energy is not changing. So we will take mgh upon T. And what is mgh? Mgh is the potential energy, gravitational potential energy. Comparison between gravitational potential and elastic potential. Now look at this screen. mgh is the potential energy in the gravitational field. Potential half Fe or half Ke square is the elastic potential energy. You can look at the comparison. The formula is there. The main concept is the same. Whatever potential energy you're talking about, it's coming from some type of work done. Potential energy is always coming from a work done. So that is the end of our quick revision. So let's a 5-minute break and then we can start our questions. A 5-minute break is there.